Hey guys, Mr. McKinney here, getting ready to do a quick review of Unit 2, which is our first unit on derivatives. First, the definition and notation for a derivative. So the derivative of a function is an expression used to calculate the instantaneous rate of change, also known as the slope of the tangent line at any given point of the function. These are just different ways to write out the derivative. If you start with y, you can call it y prime, or the derivative with respect to x of y, or dy dx. These all mean the same thing. They are the derivative of y. Or if you start with f of x, you can write the derivative as f prime of x, or the derivative with respect to x of f of x. The definition of the derivative is the same as the definition of instantaneous rate of change. So the derivative of a function can be found by finding the slope between 2 points that get infinitely close together. The distance between these 2 points is going to 0. F prime of a would be the slope of the tangent line at that particular value. And there's a different limit quotient we can use for that. So the limit as x approaches a of f of x minus f of a over x minus a. If the AP exam asks you to write the derivative as the limit of a quotient or something like that, this is what they're looking for. Keep in mind that f prime of a is not the equation of the tangent line, just the slope of the tangent line. And we'll talk about the equation of the tangent line at the end of this video. If we talk about the derivative at a point, there's a lot of different ways we can write that down. So if I start with f of x equals 1 over x, I'm looking for the derivative at the point 4. That's the slope of 1 over x when x is 4. I can write that as dy dx evaluated at x equals 4, or the derivative with respect to x of f of x when x is 4, or the derivative of 1 over x with respect to x as x is 4. These are all just notation. This is a really big one. So looking at the relationship between the original function and the derivative. So the relationship between f and f prime. If the original function is decreasing or going down, that means the slope is negative, which means that the value of the derivative is negative. If the original function is increasing or going up, that means the slope is positive, so that derivative is positive. If the original function changes direction, so when you're at the top of a hill or the bottom of a valley, at that point the slope of the tangent is 0. So f prime would be 0, and the way you would see that on a graph would be that f prime has an x-intercept. Let's look at an example. So my original function is x cubed minus x. And let's look at when the function is increasing, decreasing, or when it changes direction. So right here, my original function is increasing, so the derivative is positive. It's above the x-axis. Right here, I flatten out, so I have an x-intercept on the derivative. From here to the next place I flatten out, I'm decreasing the whole time, so my derivative is negative the whole time. When I flatten out again, the derivative should be 0, and then from here on out, I'm increasing, so the derivative is positive. Again, these relationships are really, really big. Go ahead and hit pause and try to graph the derivative if this is the original function. All right, let's see how you did. I always look for where the original function flattens out first, so where the slope of the tangent line is 0. That's going to give me x-intercepts. So 0 here. 0 here. Over here we've got 0, 0, 0. After that, I'm just looking for whether the original function was going up or down. Original function going up, that means it should have been positive. Original function going down, which means the derivative is negative. Original function going up, so the derivative is positive again. That wasn't a great graph, but you get the idea. Again here, I start going down, so the derivative should be negative, and then positive, and then there we go. The definition of differentiable at a point has 2 parts. The first thing that must be true is the function must be continuous. If the function is not continuous, then it's not differentiable, which means that the derivative does not exist. But if the function is continuous, then you need to check to make sure that the left-hand slope is equal to the right-hand slope. And the way you'd write that in calculus is you'd say the limit as x approaches a from the left of the derivative is equal to the limit as x approaches a from the right of the derivative. So if the left-hand slope and the right-hand slope are the same and it's continuous, remember there are three parts, function exists, limit exists, and they're equal to each other. Those two things must be true for it to be differentiable. Things that would make it not differentiable or non-differentiable would be corners, cusps, vertical tangents, or any type of discontinuity, whether it's removable or not. Let's look at a picture of each of those. A corner is where two linear functions meet. A cusp has at least one non-linear function, and then the slope changes instantly. It doesn't change over time. Vertical tangent would look like this. This is a cube root function shifted over. And then again, any type of discontinuity means the derivative does not exist. So the derivative does not exist here. The derivative does not exist here. The derivative does not exist here. And any place it's not continuous, the derivative does not exist. So the derivative does not exist at -6 or -4 or it does exist there because we're continuous. It does not exist at 1. Then we got into the basic derivative rule so that we wouldn't have to keep using the definition of the derivative over and over and over and over again. The constant rule says that if your original function is a constant, the derivative is 0. Power rule says if you can write the original function as a power, then you just bring the exponent, multiply it in front, and then drop the exponent by 1. And you're allowed to add and subtract derivatives. So if one function is equal to f plus g or f minus g, the derivative of that function would just be f prime plus g prime or f prime minus g prime. We also went over sine and cosine in this chapter. The AP exam included all 6 trig functions. We have learned them all, so I just put them up here as a reminder. Here's some useful math tricks that'll help you make problems easier. Remember that negative exponents just need to change from the top to the bottom or the bottom to the top. If you have a rational exponent, the number on the top is the power, the number on the bottom is the root. Remember that if you have a fraction with multiple things added together in the numerator with just one term on the denominator, you can split that into 3 separate fractions. But if you have a single term in the numerator and 3 terms in the denominator, you cannot split that into 3 separate fractions. Here's 5 practice problems. Why don't you guys hit pause and try to find the derivative of each one. All right, let's see how you guys did. Hopefully you guys remembered some of those tricks. This first one, just take the derivative of 6, goes away. Use the power rule here, -16x. For g, you'd want to break it up as 3 separate fractions, simplify each fraction, then take the derivative of each piece. Keep in mind that I have not taken the derivative until this very last step. So g, now it's g prime. The last one, rewrite it as an exponent instead of as a root. So instead of the cube root of x squared, we would say that's x to the 2/3 power. Derivative, move the 2/3 in front, drop it down to -1/3. You can leave your answer as 2/3 x to the -1/3, or you can rewrite it with the cube root of x on the bottom. Either is fine. This one, again, just write each one in the form that makes the most sense. 7 over x, write it as 7x to the -1. Take the derivative of each piece, take the derivative of each piece. If you have questions on any of these, reach out to your teacher. Second derivative, third derivative, fourth derivative, they're pretty intuitive. Just keep adding a prime. This was just notation for how to do the second, third, and fourth derivative. We'll get a lot more into these in later units. The 2 other rules that you need to learn for this unit are the product rule and the quotient rule. And they're big. They show up all over the AP exam. If you are multiplying 2 functions, you cannot just multiply the derivatives. You have to use the product rule. You are allowed to add or subtract derivatives. The sum or difference rule says you can add or subtract derivatives, but you cannot multiply derivatives. You need to use the product rule. In this case, we would say that 2x minus 3 is my u function, 3x minus 7 is my v function. So I'm going to write out what u is equal to and what v is equal to. U is equal to 2x minus 3. V is equal to 3x minus 7. Take the derivative of each of those, so u prime would be 2, v prime would be 3, and then I'm just going to plug it into the formula. I like to put v times u prime first. That way it's closer to matching the quotient rule formula, but since we're adding, you could switch the order of these terms and it won't matter. Just make sure you multiply one function times the derivative of the other function. Here's everything all worked out on that first example for the product rule. The quotient rule, which is a little bit tougher, so if your original function is u over v, then the derivative is v times u prime minus u times v prime divided by v squared. The way that I remember this formula is I always start on the bottom and I start by squaring it. So if I want the derivative of this one, f prime of x, I'm going to always start with the bottom and square it. So 1 plus x cubed squared. I don't have to actually multiply it out. I just have to write it as 1 plus x cubed squared and then put that 1 plus x cubed on the top. That's how I remember that v comes first. I do v squared on the bottom and then I put v on the top before I do anything else. Now I can find the derivative of u. U would have been on the top here, so the derivative of x would be 1 minus u, which was x. V prime, the derivative of the bottom, would be 3x squared. And then you're just simplifying, which I've done on the next step. Make sure you use the product and quotient rule if you have a product or quotient and you can't simplify it. Sometimes you're not going to have the entire function. You're going to have specific values of the function. It's the same idea. Either use the product rule or the quotient rule. I've got both of these examples worked out. I would hit pause, try to figure out what f prime of negative 3 is, g prime of negative 3, and then hit play and look at these next couple of slides. So let's see how you did. F prime, you're going to use the product rule. So just mix and match v times u prime, u times v prime. Plug in the values. And for g, we're going to use the quotient rule and simplify it down to negative 16/9. Remember that just because you see a quotient or a product doesn't always mean that you should use the product rule or the quotient rule. See if you can think about how to do these problems a little bit better. So go ahead and hit pause, try to take the derivative of each of these, and let's see how you did. This first one, you do not want to use the quotient rule. Write it as 1/8 times x, and then just take the derivative. Here, since I have one term on the bottom, I can make it 3 separate fractions, simplify each one, and take the derivative. While I could use the product rule, it's much easier to just multiply. Keep in mind that the square root of x is x to the 1/2. So x to the third times x to the 1/2 would be x to the 3.5, which is 7/2. And again, you can see these all worked out here. Couple of quick reminders that'll help you as you work through this. A tangent line or a normal line is not the derivative. The derivative will help you find the slope of the tangent line. So if you're asked to find the equation of a tangent line, use point-slope form, get the point, x1 and y1 from the original function, and get the slope from the derivative. And then just plug them into point-slope form and leave it like that. Remember that average rate of change is always going to need a slope calculation. Instantaneous rate of change is going to be the slope of the tangent line, so you're either going to use that limit formula with a quotient or the derivative rules, depending on what the AP question asks for. And remember that the derivative of position is velocity, and the derivative of velocity is acceleration. Again, I hope this video helped. Good luck as you work through all your problems this week.